Assalamu alaikum. Dear students, last time we were discussing the oxidation of the alkene using osmium tetroxide, and I told you that this lecture has not yet been completed. Today we will also study more examples, more problems related to the dihydroxylation of the alkene using osmium tetroxide. So let's continue this class. Last time we studied the mechanism of this reaction. We also studied the regioselectivity of this reaction. We also studied the stereo specificity of this reaction, and we looked into the first example of the stereo selectivity, where I mentioned an example of cyclohexanol, and this hydroxyl, it's on the front side towards you, coming out of the page, and the hydrogen was shown as a dotted line. So it means that the hydrogen is pointing away from you. So what happened there, using osmium tetroxide, we proved that dihydroxylation would occur along this olefinic double bond, and both OH will be there. That configuration will be in a major amount, where two hydroxyl are syn to that hydroxyl that is already present. And we also explained that the the presence of the polar functional group, the already present, it's been present over here, so it will decide the orientation of this OH. It will also decide the attack of this osmium tetroxide, whether it will attack from the front side of the double or it will attack from the back side. And that transition state, the stability of that transition state, will decide which stereoisomers will be in the major amount, and this is the stereo selectivity. This stereoisomer will be in minor amount and this will be in major amount. Why did it happen? Actually, when osmium tetroxide attacks from the front side, then the existence of the hydrogen bonding was actually facilitating the stability of the transition state, and that led to this product. And so this is the major product. Similarly, look into this example. Here we have this cyclohexene as a starting compound. Using osmium tetroxide, what will be the major product? Do we have a single product, or will have the two stereoisomers, or one which will be in the major and the other one will be in the minor amount? And what would be the stereochemistry of that product? Let's first discuss what is TBDMS. Actually, uh, TBDMS is tertiary butyl dimethyl silane. It's a protective group. It's called protective group. You will later in your courses, definitely you will learn what are the protective groups are. So tertiary butyl dimethyl silane, this is tertiary butyl group. dimethyl silane. It's relatively a big group, a bigger functional group, protecting group is attached to this oxygen, and osmium tetroxide has to form the dihydroxylation. Let's first draw the transition state. Those transition states will decide which will be our major product. We know that this olefinic double bond, it will act as a nucleophile. Last time another student was asking about why did not this olefinic double bond attacks over this osmium directly. Actually, no doubt osmium is electron deficient, but it actually withdrawing the electron density towards itself from all oxygen, and these oxygen atoms are getting electron deficient. So that is the reason that this double bond is actually attacks over this oxygen. Now the attack of this olefinic double bond on osmium tetroxide, or the approach of this osmium tetroxide, might have occurred from two sides, whether it can attack from the front side or it can attack from the back side. We know that this is a very bulky group, tertiary-butyl dimethyl and it is on the front side. So the attack of this osmium tetroxide would not be so easy from the front side. So where could this happen? This osmium tetroxide, the approach of this osmium tetroxide would be much easier when it will attack from the side that is opposite to this tertiary-butyl dimethyl group. So we will get two transition states. Number one, when attack is from the back side. This will be the first transition state. Let's draw another transition state. Now we have two transition states. What do you think? Which transition state would be the more stable? Here, these two, this is another a big bulky group, and TBDMS is also a very large group. So a lot of steric hindrance would be there. So this transition state is not so stable. So reaction would not direct itself to that direction where this transition state is formed. So we will get the product from this transition state as a minor product, and that transition state, which is relatively more stable, it will lead to the major product, whether this would be the major one. So this reaction is called stereo selective, or would you call it stereo specific? This is stereo selective. Selectively, we are getting this product as a major amount, another one is in a minor amount. What are the stereoselective reaction? Actually, those reaction where the already present functional group decides the stereochemistry of the two stereoisomers that are in the product. So one stereoisomer would be in the major concentration, and another one will be in the smaller one. So these reactions are called stereoselective reaction. Here I would also explain you that this osmium tetroxide is very toxic one. Osmium tetroxide is toxic chemical. Nowadays, some modification has been suggested in order to avoid the large use of this osmium tetroxide during this reaction. So people have used osmium tetroxide in the combination of NMO. NMO. And what is NMO? NMO is N-methyl N-oxide morpholine. N-methyl N-oxide morpholine. So what is the function of this NMO in reaction? Actually, osmium tetroxide, when it get exhausted, it changes into osmium dioxide. So NMO actually reconvert osmium dioxide into osmium tetroxide. So we need the catalytic amount of this osmium tetroxide to carry out this reaction. We would not use a large concentration of this osmium tetroxide, which is very much toxic and carcinogenic. So we will use it NMO with a combination of osmium tetroxide. So what is the function of this NMO? It actually regenerate this osmium tetroxide after the reaction. Okay, so you just need a minute amount of this osmium tetroxide in the reaction. We are studying the stereoselectivity of this reaction. Let's discuss another very important problem, and this problem I hope would make you learn this topic with with more confidence. You will get a more confidence while handling this problem. We are studying here a decalene system. This is our starting compound. Upon reaction with osmium tetroxide in combination with NMO. In the previous example, I have explained the use of NMO. Sometimes people also use pyridine in this reaction as a solvent. Why? Actually, pyridine or any other relevant bases, they actually stabilize the transition state. Osmium is electron deficient, so these bases actually facilitate the stability by donating the electron density towards the osmium, making the transition state more stable. This is a trans methyl and hydrogen are in opposite side. What will be the product? Whether this double bond, definitely you have to look into where the reaction would occur. So olefinic double bond dihydroxylation would occur at the olefinic double bond. Let's draw the structure, and that will help us to determine what will be the major product. This is a transdecaline. So in your previous classes, you have definitely understood the how to draw the transdecaline structure. This double bond can also be written here, and methyl is on the here and hydrogen here. Methyl and hydrogen. This Me is methyl. Methyl and hydrogen. Methyl is pointing upward and hydrogen is pointing downward. So this is the reason that this compound is transdecaline. So upon reaction with osmium tetroxide, what do you think? Whether the approach of osmium tetroxide would be easier if it attacks from the top of this double bond, or would it be much more easier for osmium tetroxide to attack from the lower phase of the double bond, where this methyl and osmium tetroxide might have the limited or the small amount of the resistance there. Actually, this methyl group, if osmium tetroxide start approaching from the upper phase of the double bond, then we will get a transition state like this. And if osmium tetroxide approaches from the lower phase of double bond, then we will have this transition state. We know that when osmium tetroxide approaches from the upper side, this upper side is called exoside attack, or when it approaches from the lower phase, lower attack is called endoside attack. So which transition state seems to be more stable? Here the steric hindrance between methyl and this osmate ester group is quite large, this making the this is making the transition state less stable. This transition state is more stable, so attack of this osmium tetroxide is more favorable when from the endoside. So after the workup, after the reduction, we get this final product. In dihydroxylation, you have to show it here like here. This methyl is on the front side, so OH are on the opposite side of this methyl. So this is your answer. Now, if your starting decalene system is cis 1, then what will be your product? on the front side. Hydrogen is also on the front side, the cisdecaline. Using osmium tetroxide, you'll have to do the dihydroxylation using osmium tetroxide in the presence of NMO in pyridine as a solvent. So what will be the major product? We will have two stereoisomers. One stereoisomer will be in the major amount. So this is another example of the stereoselectivity. You will have to draw the chair structures of this cis-decaline system. Let's draw. This is cis-decaline, and methyl is pointing upward, and this hydrogen is also pointing upward. So this is the structure of the cis-decaline. So then we will have to draw the transition states. So let's first decide whether the attack of this osmium tetroxide on this double bond is more favorable on the from the exoside or from the endoside. So here like this, we will have two transition states. Let's draw them, and those transition state will answer us which product will be in the major amount. I am drawing. So this attack is from the upper phase or the exoside. Sorry. This no, like this. I should draw again. Because it's a cis decaline system. Methyl is pointing upward and hydrogen is also pointing upward. So we will have first transition state, like, so that's designated as A. Let's draw another transition state. When the attack is from the lower phase or the endoside. So let's designate it as B. So which transition state is more stable? This transition state, which has been designated as B. Here we can see the large hydrocarbon structure is pointing downward, and large osmate ester is also pointing downward. So there would be a considerable high static hindrance between this hydrocarbon portion of the decaline system, cis decaline system, and this osmate ester, so making it less stable. So this transition state would not be possible. So the reaction will direct itself to that direction where the attack will be from the upper side or the exoside, and we will get this transition state as a in the major amount. So it will lead to the product. So what will be the product? The product will be this. dihydroxylation after reduction will be this. So in cis-decalin system, two hydroxyl group or dihydroxylation would be on the same side as the methyl. So this configuration is the most stable one as well. Although you can say that now OH methyl, they might have the considerable steric hindrance, but this would be the major one product. Why? Actually, the transition state that is leading to this product, this transition state is much more stable. Let's study some norbornene structured examples for the dihydroxylation of the norbornene structure or the bridgehead compounds. This is our starting compound. We have to react it with osmium tetroxide and with a combination of NMO and the pyridine as a solvent. And also we have another norbornene, 7,7-dimethyl norbornene, in fact. And we will have to react it with the same reagents. Remember, during the exam you should understand the reagent. You should be able to recognize the reagents. So what are the uses of this reagent, whether these reagents would create epoxidation or would they create the dihydroxylation. Remember, in the norbornene structure, these the groups at this 7th carbon, they will decide whether the dihydroxylation would occur from the exoside or from the endoside. In this reaction, in the first reaction, as there is no steric hindrance present at the 7th carbon and the osmate ester, so the attack might have occurred from either from the upper side or from the lower side. So we will have this product as a major one. Whether you can show it like here, like this one, or you can draw. So there would not be much difference in the amount of these two products, as there is no steric hindrance is present between the osmate ester and the large bulky group present at the 7th carbon. Here at the 7th carbon, at this bridgehead carbon, two methyl group, they will hinder the approach of this osmium tetroxide when it will start to approach from the exoside, from the upper side. So definitely it would, the attack of this osmium tetroxide from the lower phase of this olefinic double bond will be much more easier. So the major product will be that where these dihydroxylation occur from the lower side. So you should remember this. It will be the major product. I'm not drawing the other minor product. This is the major product. Why? I hope you will have, or by yourself you can explain why this is the major product. You should write by yourself. In the last, I'm writing another example where I will show you that if you have two or three identical reactive sites, then where the reaction would occur. I have this starting compound, and you have been asked that dihydroxylation, we need to do the dihydroxylation, the way the reaction would occur using this osmium tetraoxide, and what would be the major product. This is an example of the regioselectivity. What is the regioselectivity? In regioselectivity means that in your starting compound, if there are more than one reactive sites are present, then which reactive site is more reactive one, and you will have three different constitutional isomers, two or three, and then from them which constitutional isomer is more stable, you'll have to decide. So we have now three olefinic double bond, one, two, three. This is a ketonic group. Reaction would not occur over here. So you'll have to decide which double bond is more nucleophilic, more reactive. We know that these double bonds are the part of the delocalization. So they are not nucleophilic. This double bond is actually localized. Localized, and also it is attached to two methylene groups which have the electron donating inductive effect or the positive I effect, making this olefinic double bond more nucleophilic. So dihydroxylation would occur over this olefinic double bond. So I am just writing the major product. So thank you so much, dear students, for taking your time, for giving me your time, for understanding this lecture. I have explained a lot of examples. Then those examples would definitely would make your confidence higher. Thank you so much.